Good day everyone, welcome back to our physics series. Today we'll be discussing circular motion. Circular motion. An object moving with a uniform speed along a circular path is said to undergo uniform circular motion. Examples of circular motions are a stone tied to a string and whirled around a horizontal circle, a stone tied to a string and whirled around a vertical circle, a satellite, e.g. the moon, moving around the earth moving around the sun. Now, the magnitude of the speed of the object is constant, but its direction changes in a uniform manner. Thus, the velocity of the object is changing. This change in velocity brought about by the change in its direction constitutes acceleration. This acceleration is directed towards the center of the circular path and is called centripetal acceleration. The magnitude of the centripetal acceleration A is given by A is equals to v squared over r, where r is equals to uniform speed, r is the radius of circular path. The velocity of v at any point is directed along a tangent at that point, and we have a pictorial representation of this. For a body to accelerate, there must be a force causing the acceleration. Thus, this acceleration that is directed towards the center of the circular path is caused by a force which also acts towards the center of the circular path, that's inwards. This force is called centripetal force. Now, centripetal force. Centripetal force is that inward force required to keep an object moving with a constant speed in a circular path. It is given by the formula F of t is equals to mv squared over r, where m is the mass of the moving object. We also have what is called centrifugal force. Since centripetal force keeps the body moving in a circular path, there must be an equal and opposite force which balances this object from falling inwards. This is in agreement with Newton's third law of motion, which states that action and reaction are equal and opposite. Thus, centrifugal force is an equal but opposite force which balances the centripetal force to keep the object moving in a circular path. And we also have a pictorial representation showing both the centrifugal and the centripetal force. Angular speed and velocity. Now we have a diagram which shows or which sketches the motion of a body around a circular path. And for a diagram, we have different things that are being labeled. We have theta, which is the angular displacement, r, which is the radius of circular path, v, which is our linear velocity, s, which is the length of the arc moved, and t, which is our time. We also have other units called angular speed, which is denoted by the symbol omega. It is also called angular frequency. Now, from the diagram, if the object moves from P to Q and the radius r sweeps through an angle theta in time t, then the angular speed will be theta over t, which will make theta to be equals to angular speed times time, or omega t. Now, also the angular velocity. This is the ratio of the angle turned through to the time taken. Linear velocity v is given by v is equals to s over t. Let's call this our equation 1. If the angle is measured in radians, then s will be equals to theta r, which will be our equation 2. Now put equation 2 into equation 1. We have v to be equals to theta r over t, which will be equals to r in bracket theta over t. But we know that w is equals to theta over t, or theta over time. Therefore, v will be equals to rw. The last thing we'll be talking about is angular acceleration, which is denoted by the symbol alpha. This is the change in angular velocity over the time taken. Now, alpha will be equals to omega 2 minus omega 1 divided by t, but omega is equals to v over r from our previous formulation. So, alpha will be equals to v2 over r minus v1 over r divided by t. Simplifying, that's factorizing 1 over r out, it becomes alpha is equals to 1 over r in bracket v2 minus v1 divided by t. Now recall that acceleration a is equals to v2 minus v1 over t. Therefore, alpha will be equals to a over r, where a is in linear acceleration. Also, A is equals to V over T, which should now be equals to, replacing V with omega rho, it becomes omega rho over T, which should be equals to omega in brackets rho divided by T. But V is also equals to rho over T. So therefore, substituting, A will be equals to omega V, which should be equals to omega in brackets omega rho, which will make A to be equals to omega square rho. Up to this point, we've derived different formula for motion around a circular path and also equated them to those for motion in the linear path. Now, we'll be using this formula to solve some examples to bring this topic home. We have our very first example from NECO 2010, and it states that a stone is whirled around a circular path of radius 15 cm. If the stone makes 30 oscillations in 10 seconds, calculate the angular speed of the stone, taking pi to be equal to 3.14. And we're giving the options. Now, for our solution, one oscillation is equal to one cycle, which is equal to 360 degrees, and also equals to 2 pi radian. Now, for motions, most of our calculation involving degree, we use radian. Now, our angular speed, or the formula for angular speed, omega, is equal to theta over time. But for 30 oscillation, theta will be equal to 30 times 2 pi. Remember, we are using our radians, which should be equals to 60 pi. Substituting into omega equals to theta over time, omega will be equals to 60 pi over 10, which is equals to 6 pi. Multiplying, it becomes 18.84 radian per second. So our angular speed is 18.84 radian per second. We have another example from 2006, and it states that a body is rotating in a horizontal circle of radius 2.5 meter with an angular speed of 5 radian per second. Calculate the magnitude of the radial acceleration of the body, and we're giving the option. Now, for our solution, radial acceleration A is equals to omega rho, and omega equals to our angular speed, in this case is 5 radian per second. Rho is the radius of the circle and it's 2.5 meters. So substituting, A will be equals to 5 squared times 2.5, which should be equals to 25 times 2.5, which is equals to 62.50 meter per second square. We have another question from NECO 2005, and it states that a body moves along a circular path with uniform angular speed of 0.6 radian per second and at a constant speed of 3 meter per second. Calculate the acceleration of the body towards the center of the circle, and we're given the option. Now, from our formula, acceleration is equals to omega square rho, but in this case, we're not given the value of rho, so we'll be using value for V and W to get rho, then substituting rho into the original equation. We know that V is equals to omega rho, where V is our linear velocity and it is given as 3.0 meter per second, and omega is our angular speed and it's given as 0.6 radian per second. Now, rho is the radius of the circular path, so it will be equals to V over W, which is equals to 3 divided by 0.5, which is equals to 5 meter. Now, since we've gotten the value for rho, we can now substitute into A equals to the omega square rho. Doing so, A will be equals to 0.6 in bracket square times 5, which is equals to 1.8 meter per second square. We have our final question from NECO 2014, and it states that a body of mass 12 kg moves with a speed of 10 meter per second in a circular path of radius 5 meter. Calculate the magnitude of the force acting on the body, and we're given the option. Now, for our solution, since the body moves in a circular path, the force acting on the body is centripetal force, which is Ft. Now, Ft is equals to mv squared over rho, where m is the mass of the body, and in our question is 12 kg. V is the speed of the body, given as 10 meter per second, and rho is the radius of the circular path, given as 5 meter. Now, substituting, Ft will be equals to 12 times 10 squared divided by 5, which should be equals to 12 times 100 divided by 5, which will then be equals to 12 times 20, which is equals to 240 Newton. Here are some exercises for you to try your hands on at home. And for more insight on this topic, you can check out the chapter 2 of our Hidden Fast Physics textbook. You can get the hard copy in bookshops, or if you are interested in the soft copy, you can get it at the website on the bottom of the screen. Thank you.